Article 400.9 of the 2002 National Electrical Code, NEC, states that taps shall not be made to any conductor carrying over 100 amps. This rule is crucial for ensuring electrical safety, especially in temporary power setups like those found at construction sites. In the scenario described, we have 20 to 25 well pumps, each reported to be 1 horsepower, powered by a temporary generator. The primary cable, a hard service cord type SU, is routed along the ground, and secondary cables with receptacles are tapped onto this primary cable to power each pump. Fundamental problem here lies in the accumulation of current. The primary cable carries the current for all the pumps. If the combined current draw of these pumps exceeds 100 amps, the described setup violates NEC Article 400.9. To determine if the 100 amp limit is exceeded, we need to calculate the total current draw. Firstly, we need to determine the full load current of each 1 horsepower pump. Assuming these are 120 volt pumps, we can estimate the full load current. A 1 horsepower motor at 120 volts typically draws around 16 amps according to NEC Table 430.248. Now, let's consider a scenario with 20 pumps. If each pump draws 16 amps, the total current would be 20 pumps multiplied by 16 amps per pump, which equals 320 amps. This is significantly over the 100 amp limit specified in NEC Article 400.9. Even if the pumps are 240 volt, the amperage would still likely exceed 100 amps. Secondly, with 240 volt pumps drawing approximately 8 amps each, 20 pumps would draw 160 amps in total, still exceeding the limit. Therefore, the taps made to the primary cable to power these pumps are indeed in violation of this article. The continuous primary cable, serving as a series of taps for each well pump, creates an unsafe condition when the total current exceeds the limit. A better and more code-compliant approach is needed to ensure the safety and reliability of the temporary power distribution system. Instead of direct tapping, consider the following alternative. Firstly, using a raceway or cable tray system for the primary cable run. Secondly, tapping off the primary cable at each pump location using junction boxes or similar approved devices. A raceway system such as conduit or a cable tray provides physical protection for the conductors and a dedicated pathway for the wiring. This minimizes the risk of damage to the cable, which is particularly important in the harsh environment of a construction site. It also allows for better organization and management of the wiring. At each pump location, install a junction box. This junction box serves as a safe and enclosed point for making electrical connections. Inside the junction box, use appropriately sized and rated connectors to tap off the primary cable. This ensures a secure and reliable electrical connection. Each tap should be protected by an overcurrent protection device, such as a circuit breaker or fuse, located within the junction box or at a distribution panel. The size of the overcurrent protection device should be matched to the ampacity of the conductors and the requirements of the pump motor. Reference NEC Table 430.52 for motor overcurrent protection. For example, if the pump motor has a full load current of 16 amps and uses an inverse time circuit breaker, the maximum rating of the breaker would be 16 amps multiplied by 2.5, which equals 40 amps. Select a standard breaker size at or below 40 amps. A distribution panel or power distribution block can be used to consolidate the overcurrent protection devices. This panel can be located near the generator or at a central point within the construction site. Distributing power through a panel allows for better control and monitoring of the electrical system. Each circuit can be individually protected, and the panel can be equipped with meters to measure voltage and current. A feeder cable supplying power to the distribution panel must be sized according to NEC Article 310.15, which covers ampacity requirements for conductors. The feeder cable must be rated to carry the total load of all the pumps, plus any additional loads connected to the panel. Additionally, consider directing factors for ambient temperature and the number of conductors in a raceway. For example, if the total load is 320 amps and the ambient temperature is high, You may need to upsize the conductors to compensate for the temperature darting. Proper grounding is essential for electrical safety. Grounding ensures that in the event of a fault, the current will safely return to the source, tripping the overcurrent protection device and preventing electrical shock. Ground all metal enclosures, such as junction boxes and the distribution panel, in accordance with NEC Article 250. Use a grounding electrode system that complies with NEC requirements, such as a ground rod or connection to a metal water pipe. Equipment grounding conductors, EGs, must be run with all circuit conductors to provide a low impedance path for fault current. Ground fault circuit interrupters, GFCIs, provide an additional layer of protection against electrical shock. GFCIs monitor the current balance between the hot and neutral conductors. If there is an imbalance, which indicates a leakage of current to ground, the GFCI will quickly trip, interrupting the circuit. NEC Article 590.6 requires GFCI protection for all 125-volt, single-phase, 15, 20, and 30-amp receptacles used for temporary power at construction sites. This includes receptacles used to power the well pumps. The SU cable itself, while suitable for flexible cords and portable applications, may not be the best choice for the primary distribution cable in this scenario, especially when it is laid directly underground. Direct burial cables or cables approved for use in cable trays or raceways offer better protection against physical damage and environmental factors. Consider using type use, underground service entrance cable for direct burial applications, or type TC, tray cable for use in cable trays. These cables are designed to withstand the rigors of construction site environment. All electrical equipment used at a construction site must be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, UL, or Electrical Testing Laboratories, ETL. Listing and labeling indicates that the equipment has been tested and found to comply with applicable safety standards. Ensure that all cords, cables, connectors, and other electrical components are properly rated for the voltage, current, and environmental conditions in which they will be used. Use weatherproof or watertight enclosures and fittings where necessary to protect against moisture and dirt. Regular inspections and maintenance are critical for ensuring the ongoing safety and reliability of the temporary power system. Conduct routine inspections to check for damaged cords, loose connections, and other potential hazards. Repair or replace any damaged equipment immediately. Use qualified electrical personnel to perform all electrical work. Only trained and experienced electricians should install, maintain, and repair electrical equipment. Ensure that all personnel working on the construction site are aware of the electrical safety procedures and potential hazards. In summary, the initial setup described violates NEC Article 400.9 because the taps on the primary cable likely exceed the 100 amp limit. The recommended alternative involves using a raceway or cable tray system, tapping off the primary cable through junction boxes with overcurrent protection, ensuring proper grounding, using GFCI protection, selecting appropriate cables, and conducting regular inspections and maintenance. By following these guidelines, a safer and more code-compliant temporary power distribution system can be established at the construction site. In addition to the NEC requirements, it is essential to comply with all applicable local electrical codes and regulations. Local codes may have additional requirements or restrictions that must be followed. Consult with a local electrical inspector or qualified electrical engineer to ensure full compliance with all applicable codes. The layout of the temporary power system should be carefully planned to minimize the risk of accidents and injuries. Keep cords and cables out of walkways and areas where they could be damaged by equipment or vehicles. Use cable ramps or bridges to protect cords and cables that must cross walkways or roadways. Clearly mark all electrical equipment and wiring with appropriate warning signs. Provide adequate lighting in all work areas to improve visibility and reduce the risk of accidents. Consider the voltage drop in the conductors. Voltage drop occurs when the voltage at the load is less than the voltage at the source. Excessive voltage drop can cause equipment to malfunction or overheat. To minimize voltage drop, use appropriately sized conductors and keep the length of the conductors as short as possible. Reference NEC Chapter 9, Table 8 for conductor properties. The formula for voltage drop is voltage drop equals 2 times K times I times D divided by circular mils, where K is the constant representing the direct current resistance for 1 circular millifoot of conductor, I is the current in amps, D is the one-way distance in feet, and circular mils is the area of the conductor. The NEC recommends that voltage drop should not exceed 3% for power, heating, and lighting circuits, or 5% for feeders plus branch circuits. Consider the impact of harmonics on the electrical system. Harmonics are distorted waveforms that can cause overheating of equipment, nuisance tripping of circuit breakers, and other problems. Nonlinear loads such as electronic ballasts and variable frequency drives are a common source of harmonics. To mitigate the effects of harmonics, use harmonic filters or reactors. Ensure that the electrical system is properly designed and installed to handle the harmonic currents. The NEC provides guidance on harmonic mitigation in Article 220.61. Furthermore, document all aspects of the temporary power system. This includes the layout of the wiring, the size and type of conductors, the ratings of overcurrent protection devices, and the results of any inspections or tests. Maintain accurate records of all maintenance and repairs. Documentation is essential for troubleshooting problems and ensuring the long-term safety and reliability of the electrical system. Regularly train workers on electrical safety procedures. This training should cover topics such as the hazards of electricity, the proper use of electrical equipment, and the procedures for reporting electrical problems. Ensure that all workers are aware of the location of emergency shut-off switches and the procedures for responding to electrical emergencies. Training is essential for preventing accidents and injuries. Consider using a load bank to test the generator. A load bank is a device that simulates an electrical load. Testing the generator with a load bank ensures that it is capable of providing the required power and that it is operating properly. Load bank testing can also help to identify potential problems with the generator before they cause a failure. Properly size the generator. The generator must be capable of providing sufficient power to meet the demands of all the connected loads. Consider the starting current of motors and other inductive loads. The starting current can be several times higher than the running current. Ensure that the generator has sufficient capacity to handle the inner current of these loads. Consult with a qualified electrical engineer to determine the appropriate size of generator. Remember that electrical safety is paramount, and adherence to the NEC and local codes is not just a legal requirement but a moral one, protecting workers and preventing accidents on the construction site.